Module 2 may be the smallest of the three modules in terms of chapters covered, but still deals with topics that are utilized quite a bit in our culture today. Collectively, the topics covered fall under the general heading of electromagnetic radiation and optics. Chapter 22 deals with topics related to the first of two competencies covered in this module. Define the concepts of electromagnetic waves and the electromagnetic spectrum. Here the concept of electromagnetic radiation is introduced, including the use of different wavelength bands. Depending on the size of the waves and the corresponding frequency, there are lots of different applications to different parts of the electromagnetic spectrum. The product of the wavelength and frequency of a particular electromagnetic wave gives its speed, the speed of light. In a vacuum, this represents the fastest speed we know of, but when an electromagnetic wave passes through a physical medium, it is slowed. The index of refraction for that particular wavelength of light is the ratio of the speed of light to the speed of light in that medium. Different materials have different indices of refraction depending on the wavelength of that electromagnetic radiation passing through. Because we are talking about waves, the description of the motion of the electric and magnetic components of an EM radiation can be described mathematically using wave equations, first introduced back in Physics 201, College Physics 1. It might be good to go back to those relevant chapters in the textbook and review wave equations and what information about a wave can be gotten from those equations. Properties of waves would include the energy transported by the wave, the intensity of the wave, polarization or the orientation of the electric component of the EM wave, and the Doppler effect, the effect on the observed wave based on whether the object is moving toward the observer or away. The Doppler effect was covered when it came to sound wave as well back in College Physics 1 and might merit review of that concept. Chapters 23 through 25 collectively deal with the second course competency covered in this module. Solve problems both graphically and mathematically in geometric optics. Chapter 23 looks more at the wave nature of electromagnetic radiation, looks specifically at phenomena known as reflection and refraction. Reflection of wave deals with the energy of the wave when confined to the same medium. The law of reflection states that the angle made between the direction of the incoming radiation to a normal drawn perpendicular to the surface is the same as the angle of the direction of the outgoing or reflected radiation with respect to that same normal. Snell's law is used when looking at the refraction of EM radiation as it moves from one medium into another. Depending on the index of refraction of each medium, the direction of the EM radiation can be changed. In particular, when going from a less optically dense medium to a more optically dense medium, the path has been closer to the normal upon entry. But if the light source is in a more dense medium, such that the light is moving toward a less dense medium, it becomes possible, at the correct angle, to trap the light within the more dense medium, what is known as total internal reflection. Such process can be exploited in the use of fiber optics, used in a variety of technologies today, or to simply explain the prismatic effects of a diamond. Chapter 23 also looks at the possible image formation that can result from either reflection or refraction. Plane mirrors, for example, can produce images referred to as virtual images. These are images that to our eyes seem to be there, but light is not actually passing through the image seen. For plane mirrors applying the law of reflection, one finds that the virtual image appears to be as far behind a mirror as the object providing the light is in front of the mirror. Things change when curvature is added to the reflecting surfaces. Mirrors can be bent inward or outward, and each type will produce different types of images. If a mirror is bent inward, say in the shape of a partial surface of a sphere, then it is referred to as concave. If it is bent outward under the same conditions, say the shape of a partial surface of a sphere, then it is referred to as convex. Depending on the type of mirror and the location of the object from which the light comes, these mirrors can produce both virtual and real images. Real images are those through which the light actually passes, unlike virtual images mentioned earlier. These image production processes can also have broad application. Refraction can also be exploited through the use of lenses. Like mirrors, the shape of the lens determines its type. Simple lenses that could be thought of as the outer partial surfaces of spheres are referred to as convex lenses. Those that can be thought of as the inner partial surfaces of spheres are referred to as concave lenses. And, like spherical mirrors, spherical lenses can produce either real or virtual images, depending on the type of lens and the location of the light source. Chapter 24 continues with the application of lenses of mirrors in a variety of objects found today. The human eye uses a natural lens to produce images of objects in its surroundings on the retina. Out of roundness can result in symptoms such as nearsightedness or farsightedness. Cameras can use both lenses and mirrors in the production of images, either collected on photographic emulsions or, more recently, on chips for electronic storage purposes. Microscopes can use lenses to be able to bring the small world into view to the human eye. And telescopes can reveal to the human eye the wonders of the universe, using lenses and or mirrors to gather and focus the light from those distant objects. Chapter 25 explores wave phenomena known as interference and refraction. These phenomena are uniquely wave-related and were helpful in providing experimental evidence that light, and by extension electromagnetic radiation, could be explained as wave phenomena. Thin films can be observed to affect the light falling on them by producing arrays of colors. Interference of light rays falling onto the surface or passing through the surface and reflecting back out again helps to explain the colors that you see or not see, depending on the wavelength and thickness of the film. Young's double slit experiment clearly showed how a single wavelength of light could result in a sequence of bright and dark bands of that wavelength, explainable only if light was a wave or had wave-like properties, interference in this case. This has been exploited in the creation of gratings that can break light up into component colors just as a prism does. Reflection gratings and transmission gratings are used in a variety of ways in both research and entertainment. Diffraction, the bending of the direction a wave travels when going around a solid object, was also used to demonstrate the wave nature of light, and has further application in understanding the resolution of optical devices and observations at other wavelengths than that of light, such as X-rays. So Module 2 may be the smallest of the modules covered in this class, but does cover a broad range of topics. Many of the topics covered have applications in our world around us, technologies exploiting the wave nature of electromagnetic waves. Most of that has been in visual portion of the EM spectrum, but application of the use in other wavelength bands also plays a role in our everyday lives.